And now it is my pleasure to introduce our first keynote for the day, Dr. Omer Artoun. He is the CEO and founder of Agile One Predictive Marketing Cloud, which is a venture funded by top-tier venture capital firms such as Sequoia Capital and Mayfield. He holds a PhD in computational neuroscience and physics from Brown University, where he studied under Nobel laureate physicist Leon Cooper. Before he founded Agile One, Dr. Artoun was a high-tech consultant at McKinsey, VP of Strategic Marketing at CDW and Micro Warehouse, Senior Director of B2B Marketing at Best Buy for Businesses, and Adjunct Professor of Marketing at NYU Stern School of Business. Today, Dr. Artoun will be sharing some of his expertise with us as he discusses how companies can use predictive analytics to personalize marketing strategies. We're all going to learn how to use machine learning technologies to best engage our customers. And now, Dr. Artoun.
Thanks, everyone. I was amazed by some of the students, how well they were prepared and some of the techniques they're using. It's amazing to see how at a young age they're so advanced. I'm going to keep my talk at a little bit of a high level to talk about machine learning and what inspired me to get into it and what we're doing with it, how we apply it into business. So for that, I'm going to talk about predictive marketing, which is an application of deep learning in marketing into a business context. I also want to say that I'm the father of Leila Artoun. She's a class of 2022. And I'm also the uncle of 4 other kids, Yağmur, Deniz, Emre, and Dilara. So that explains why I have to work for a long, long time. So I'd like to tell you a little bit about myself and how I got inspired and got into this field. So I've received my degree in electrical engineering, and after that I started doing my PhD in physics at the University of Maine. And one of the classes I took was about fuzzy learning and neural networks. And I read an article there written by Leon Cooper, who was a physicist at Brown. And I was really moved by it. And I'll explain why. It was all around the transition that was happening to build biologically inspired networks that kind of shattered the traditional wisdom of structured programming. Rather than writing instructions, you would basically let the computer or the system configure itself, which is kind of an intelligent system. So I've gone to work, did my PhD with Leon Cooper. We did a lot of research funded by Office of Naval Research, trying to detect mines, underwater mines for submarines, down to handwriting recognition. And this is all happening in the early 90s, so you could imagine, we were using Spark stations at the time, and now your handheld devices have more power than that. So there had to be a lot of computational and crunching efficiency that you needed to bring. After my PhD, I wanted to apply this machine learning. I was fascinated by it. I said, how can I take my learning in mathematics, and I looked around to my friends who was in business. They were still dealing with spreadsheets and kind of simple math. And I said, how can I apply this? This is a revolutionary thing that's going to transform many, many industries. I said, how do I get into business? Because I don't want to be in academia, and I'm too practical of a person. How do I apply this to business? And somebody said, well, you should go work at McKinsey, because they'll fast forward you into the business world, and you can understand what problems the businesses are trying to solve. And I've done that, and out of that, I've realized that one of the areas that really could benefit machine learning and predictive analytics is where the businesses are dealing with really complex situations. And the most complex situation a business deals with is their customers. So I thought I could really apply, this concept of machine learning using data from consumers to better predict what they're going to need, make marketing relevant, make better spend decisions around marketing, and that's why I founded Agile One. It's been about 10 years. We've been venture funded by Sequoia, Mayfield, and I've also recently wrote a book about predictive marketing, of how to apply this predictive science into marketing, which we'll be presenting at the desk a little later on. So like I said, my company applies the data science to marketing, and it's all about increasing the relevancy of the marketing that we see today. In today's world, there are many, many marketing touches that we get. We get hundreds of emails. We go to different sites. We get ads. When we call the call center, we get treated differently. And there are certain companies that apply this really, really well. If you interacted with Amazon or Netflix, they're all companies that are in the really forefront of applying data science to marketing. And you can feel that. You can feel that in your interactions and so forth. And what we're trying to do is to take this data science and make it available to all companies. So my company is about a 130-person company. We have offices here. Our headquarters are in Sunnyvale, and we have offices in New York, London, and Istanbul. And about 15 of those people are data scientists that are developing algorithms and not just developing algorithms to solve a specific problem, but again, the company that we have, we serve over 200 customers. So our challenge is a little bit different in the sense that you have to build algorithms that learn, but also algorithms that in and of themselves, they adapt to different customers, right? So we are serving customers like Starbucks and Hugo Boss and Lululemon, and their customers and their marketing environments are completely different. So you need to build, environments that not just learn, but the environment itself is a learning environment. So that presents a bit of a challenge on how do you make this as a scale software company without, solving specific problems for a customer. And towards the end, I'll talk a little bit about one of the problems that we solve, just at a high level, so that it gives you a flavor of what the application is and what the outcome of this is. But before that, I'd like to start with what inspired me. So, as I said, when I was doing my master's, I read this article by Dr. Cooper in the Neural Network Concept Applications and Implementations back in 1990. And I was really inspired by it. And he's been working on this problem since he got his Nobel Prize in '72. He looked into, sorry, let me rewind back. Dr. Cooper was one of the people that solved the problem of superconductivity. Superconductivity was discovered in the early 1900s, and Niels Bohr, Einstein, many people tried to explain the phenomena theoretically and couldn't. And Dr. Cooper once told me, said, if I knew Einstein and Bohr couldn't explain it, why would I, track that problem? But he was able to solve this problem with Bardeen, John Bardeen, who was also a Nobel laureate professor, who was the guy who founded transistor, which many of you knows that it kind of transformed the whole electronics industry. And after Cooper got his Nobel Prize, he said the next frontier, that the next big unsolved problem in science is the brain, and how brain works, and how we can apply the learnings from biological networks into mathematics and understand, how we can solve complex problems like handwriting recognition, like facial recognition, and many other problems. And I was really inspired by by the article that I read, that I switched, schools, and I went and worked for him to get my PhD in computational neuroscience and physics, building biologically inspired neural networks to learn and detect certain things. Again, with some of the algorithms that people were talking about. For example, in our times, we didn't have the convolutional neural networks. I work with Jeffrey Hinton, who's one of the the forefathers of deep learning, with Dr. Cooper, and at the time, we tried to crunch the data on much smaller computers, and I can tell you many stories about that. And there's one other fun fact about Dr. Cooper, is that he is the name of Sheldon Cooper in Big Bang Theory is named after Dr. Cooper. which is a really fun fact for me. I'm going to show a really short video. It's about a minute long. This is 1985.
A computer is a system that can execute large numbers of instructions with accuracy and incredible speed. And in order to get him to do something, the idea has always been to write a program with these large numbers of instructions. But when you have a real world problem, let's say like riding a bicycle, if you think of the number of instructions one would have to write to handle every situation that you might encounter, you see that although it's not impossible, it becomes backbreaking. Has it been the pattern that we're following in the history of computing development by and large? Probably the strongest trend, the dominant trend among computers has been the attempt to write complex programs to solve real-world problems. There are no other trends we can't really develop in this specific time, but our point of view has been that animal systems, including humans, learn partially by having a set of instructions, but the most important part of our learning seems not to come via an explicit set of instructions. It seems to come via being placed in real-world situations and learning by the experience. And what we thought was the thing that was most lacking in the systems that existed was this capacity to learn by experience. Now, our systems can have explicit instructions written into them, but in that sense, they're not different from conventional systems. The single marvelous new feature they have is the ability to actually learn without having the instructions explicitly written.
Okay, so that was a short video of Dr. Cooper in 1985 talking about neural networks, how it's biologically inspired. And this is a year before the most famous artificial neural network, which is called the backprop algorithm, that some of you might know, was kind of developed by David Rumelhart up in Stanford. And again, they've been working on this problem since like the early 70s to figure out the biological inspiration of how these things work in the brain, so that they can develop algorithms that mimic that. And now, fast forward 30 years, we have amazing applications of this, from facial recognition to, personality matching and so forth. There are many, many applications for it. And one of the things that Dr. Cooper kind of talked about was the difference between the approaches. In regular programming approaches, you have a set of instructions that are set in the system that you go through, and you have to lay out all the options, all of the decision tree. You have to cover all of the exceptions, and this is really good for certain type of problems that humans might not be good at. But there are another set of problems that this type of instructions, structured programming, doesn't really solve, and it is really terrible at it. So first of all, I also want to talk a little bit about, I use the term machine learning. You might have heard many, many different terms like predictive analytics, pattern recognition, artificial intelligence, data mining, deep learning, and so forth. But each of these things are kind of referring to the similar concept. A lot of these terms have changed their meaning over time. Artificial intelligence was, in the early days when I was doing my PhD, was done by kind of MIT guys writing a bunch of code that was much more instructive code that didn't really learn, but it kind of it was a nonlinear system that was programmed in. And now the word artificial intelligence is used in general, overall intelligence. And same thing with like neural networks and pattern recognition. Pattern recognition sometimes refers to things that are not doesn't have target variables, but you're trying to recognize patterns without. So it sometimes refers to kind of unsupervised learning and so forth. But in general, everybody's trying to say the same thing, which is, can we build something without an explicit set of instructions, that the instructions kind of build themselves, is the whole idea behind this. And the early versions of this started with, the first computer was built by Alan Turing. As some of you might know, he cracked the code on Nazi communications during Second World War. And then if you haven't watched the movie Imitation Game, it's an amazing game. I would recommend all the students to watch it as well. I don't know if it's rated R, but I think it's an amazing movie. And one of the things that Turing has said was, can computers become intelligent? After he built the first computer, he said, can we build computers that are intelligent enough that the humans can't tell whether it's a computer or a human behind it? Because if you can't tell them apart, then you can basically claim that the computer is intelligent. And he came up with this thing called the Turing test. And some of you might know this, but Turing test is if you put a curtain and put either a person or a computer behind it, and behind the curtain, in front of the curtain, somebody asks questions, and either the computer or the person is giving answers, can the observer, without seeing who's giving the answer, can they tell with a certain level of accuracy whether you can determine if the thing is a computer or a person? And this is still a very intelligent thing. I mean, all the things they talk about at IBM, at Watson, and so forth, it all evolves around this level of thinking. Can we build a system that a human cannot tell apart? And one simple application of the Turing test is, you feel it in your everyday lives. When you go to a website, they ask you to type in certain things, or you have to click a box that says, I'm not a robot. And this is called a CAPTCHA test. And CAPTCHA is actually the acronym for the completely automated public Turing test to tell computers and humans apart. And when you look at this image, a human can easily see that it's SMWM, but for computers, it's really, really hard to recognize this. And there are reasons for that I'm going to talk about a little bit. There are certain tasks in real life, like programming a video game or calculating tax for payroll, counting votes, or serving web pages, and so forth. These are tasks that are super easy for structured programming that you can write because you're doing things over and over again. But it's super hard for humans to do in a fast and accurate way. But let's switch to other problems that are a bit more complex. Things like sentiment analysis. If you read an article, whether it was positive or negative, or was it a satire, or handwriting recognition, or self-driving cars, or personality matching, and each of these things have applications in real life that we experience. But these are problems that are super easy for humans, but it's really, really hard for computers to do. But why? What's the reason for these? If you look at these tasks, what are the differences between these tasks from the previous mundane tasks that make them so difficult for computers? One is there are too many exceptions. In any sort of computer programming, you have to account for every single path to go through because the computer program just repeats itself. Whatever you tell them to do, it'll do the same thing over and over again. It does not evolve, it does not learn, it doesn't change. Second thing is there are too many parameters. There are too many degrees of freedom in a complex system for you to be able to comprehensively program against it. And that degrees of freedom is what crushes any sort of approach to structured programming to solve these complex problems. There are always 2, 3, 5, 10, 20% of the cases where the structured programming will not solve. Third thing is changing underlying system. This is also a huge problem where if you're trying to detect something, whether the background, if you're trying to detect a face, the background changes over time, the face ages, they might be wearing a makeup the next day it might be a hat, and so forth. It becomes really difficult if the underlying thing that you're trying to determine or solve for have changes over time. A fourth problem is representation. So humans have a great way of taking the data and representing it in a specific way. So in our eyes, we take our receptors see this. This is was part of my research, visual cortical research at Brown. Our eyes take the data in a very kind of linear way, which is receptors in the back of your eye. Retina detects it. It then goes through a compression algorithm in lateral generative nucleus, and then goes into visual cortex, and visual cortex have layers, V1, V2, V3, and the information gets represented indifferently and gets compressed and processed. And through this thing, the representation changes over time. So the data that you're seeing doesn't stay constant in the system. It gets transformed constantly. Whereas the data, the input data into a program usually is the same data over time. One of the last ones is the trade-off. So the structured programs don't have the ability to trade off different cost functions. So it's usually good at making determinations on a equal or greater than or less than equal basis. But by taking multiple dimensions into account, it's hard to have this linear boundaries of decisions of yes and no is really, really hard for structured programs. And then the last one is noise. So in real life, there's so much noise, like background, sound, the color, lighting, all of those things, if you're trying to recognize an image, that presents a huge problem for structured programming. Whereas for us humans, I can recognize my daughter or my wife like super easily in any light condition or any situation. So this comes up to our next topic, which is, to solve these problems, you have to have intelligence. By having intelligence, it solves these problems very, very elegantly. So then you have to ask yourself, what is intelligence? Intelligence is a two-step process. It's about assimilating data, and then it's basically adapting to it. And this is how humans do it. We constantly take data inside, learn about it, adapt ourselves to it, so next time we encounter it, we have a different result against the same data. And in the computer world, this is about, the assimilation is about data cleansing, standardization, representation, and noise handling, and so forth. And then the adaptation phase is machine learning. And I'll talk a little bit about what most of the approaches to machine learning is focused around the algorithms themselves. Actually, the assimilation phase of this, in my opinion, it has much more impact on the outcome than the specific algorithms that you use. And when you look at the intelligence of humans, there are certain heuristics. So if you're going to build a system that's going to mimic human intelligence, that system has to have built-in heuristics that a human intelligence does. And there are many, many heuristics of human intelligence, and I'm just putting some of them up here. I won't mention all of them, but one of them is anchoring. Anchoring is a human heuristic that we constantly compare the past to the future and basically determine it's a difference algorithm. We don't, if something is not changing, we don't detect it. Second one is calculation of probabilities. When you're driving, you constantly look at, okay, if there's a car coming that way, I calculate the probability whether it's going to hit me or not. If not, I basically move on. Representativeness. Humans naturally group things together. They cannot deal with individual complexities. They automatically group people together. That's why, humans constantly generalize, different, races of people, different car types, different, different building types, and so forth. This is how we deal with complexity. We try to represent it in a group way. And then there's another heuristic called gains and losses. So people, one of the heuristics that humans have is that we do not want to lose. We actually hate losing more than what we like winning. And that's a great mechanism because negative reinforcement is basically what's keeping the humans learning much faster. The positive reinforcement, you expect, you learn something from it, but the negative reinforcement, the fear of losing, the fear of making mistake, is much bigger than the joy of this. So they've done some research. Actually, there's a book I would highly recommend if you guys are interested in some of this thing called, how they can influence people to make decisions or how people make decisions. It's a book called Nudge that talks about this whole human intelligence very, very elegantly. So they've done some research to say that people are 2 times more miserable than losing an item than gaining that item. And then last one is framing. So framing is about how information is represented. How you take data and represent it in your head is important. So for those of you who are math majors, you can take 2 points on a Cartesian axis that are really close together, around the x-axis, and you can say, okay, these points are close together. But if you take those 2 points and represent them in the radial world, you would basically say these points are the farthest apart because one is like right around 0, the other one is right around 2 pi, and the representation makes a huge difference on how you perceive data. So things like, for example, if I told you that somebody's going to have a surgery and 1 out of every 10 patient that walks in that door is going to die, versus if I tell you 90% of the patients live, you think that 90% is pretty good, and 1 out of 10 people dying is really bad, right? So how you frame the data is really important, and it all comes to that point of assimilation of the data before you adapt to it. And all of these things are built into our human genetics and how we operate. And it's about machine learning is about taking these heuristics and understanding from biology to adapt and to build systems that evolve and are intelligent. I'll tell you a little bit about, for those of you, how neural networks and how some of the machine learning algorithms came into play. It's all about biologically inspired. So if you think of a neuron, which has dendrites and synapses that connect, and then there's an axon that makes a connection to another neuron. There are billions of this in our brain. What happens is that if synapses get potentiated, so there's a signal coming through to a synapse, and if this synapse gets potentiated all around the same time, the nucleus of the cell gets potentiated above a certain point, and at that point the nucleus fires and creates another signal that makes a connection to another neuron. And if this happens more and more often, the synapses get stronger. So, the synaptic strength, if the neuron fires right around the same time as synapse gets potentiated, that synaptic connection gets stronger and stronger. And this is how we learn in our brain. And if you take this to a mathematical model, it's basically a set of matrices that you can set up. So there's synaptic transmission coming in, which is connected to neurons, which is connected to another set of neurons. And these weights between the matrices, the matrix components, represent the weights between each layer of neurons, represent the synaptic strength, which is biologically inspired. And then there are algorithms that basically say, okay, if the final signal is matching or is firing at the same time as the synaptic firing or the pre-neuron firing, then what I'm going to do is I'm going to increase the weights. If they don't, then I'm going to decrease the weights. And this is how this system learns. So, this is an example of how some of these systems are really learning from data. And machine learning, there are multiple modes of learning. There's something called supervised learning, which is a set of algorithms where it's looking at a target variable. So, for example, in our company, we have a model called propensity to buy. So for every customer, based on their web behavior, prior purchase behavior, and other factors, we're trying to predict whether they're going to buy or not. And the way we do that is by looking at other customers that have exhibited a behavior and then bought something, and that kind of feeds the system and learns it. Unsupervised learning is about, you have let's say I have a room full of people like yourself, and I'm trying to determine what are your likes or dislikes around different sports, right? So now I don't have a specific outcome that I'm trying to predict. All I'm trying to do is, take a heterogeneous group of people and put them into groups that are homogeneous, and that's unsupervised learning. And then there are other methods like semi-supervised learning where you're gonna supervise the learning process, but you don't have that input all the time. So, for example, you're learning to drive, and sometimes you go out with your parents, sometimes you go out with a teacher, but you don't have you're not going out to learn every single time. Sometimes you're trying it yourself. So in that imperfect teacher scenario, it's called a semi-supervised learning. And reinforcement learning is another method where you're basically getting feedback from every prediction you make, and it's an iterative learning process where you're getting a positive or a negative stimulus, and that makes the system evolve and get intelligent over time. I want to talk a little bit about the machine learning process, because when I look at the young people that are getting into the field, and when I hear about all the talk in the industry about every company is now using machine learning, one of the things that machine learning is a process. It has multiple steps into it around data collection, feature generation, feature extraction, and so forth. And it goes through a learning training process, champion challenging process, scoring, QA testing, and retraining. What I usually see is the yellow box that is out there. Most people focus on the classifier design, which is what algorithm are we using? Are we using Boltzmann machines, or are we using linear regression or random forest trees and so forth? But the biggest impact that the success of a machine learning process is to follow this whole process, and it has many, many steps to it than just applying one algorithm to it. In my opinion, just like we talked about assimilation and adaptation, in the assimilation process, how you represent the data is, in my opinion, has a bigger importance than classifier design. In this field, there's something called the no free lunch theorem, which basically says there's no one algorithm that's superior across different set of problems. And each problem needs to be taken into account on how you process the input data and which algorithm do you use. And you need to be careful about that. And that's in machine learning, there's an art to it, and that art comes in this kind of feature generation stage. If you're trying to predict whether somebody's going to buy, use the pro shop in a golf course, you might need different set of data to be inputted in the system than if you're trying to predict, cancer detection and so forth, in terms of how you represent the input data. Again, sometimes, what I mean by this is sometimes you can take absolute values, sometimes you take ratios, sometimes you might take the logarithm of a number, and so forth. All of these things have a huge impact on the accuracy of the outcome. So I'll talk just a few minutes about a specific problem that we solve in our company, just to bring it to home and make it concrete for you. And before I do that, as a business, I believe in something different than artificial intelligence. There's a lot of talk around machines taking over and making all the decisions, but there's another approach to all of this, which is called intelligence amplification. So if you go to Wikipedia, you can read about this, which is a very intelligent topic. But the whole concept is that machine learning is a great thing to aid in certain things, to basically package things up. But there's a human element to this of how we can make decisions that the machine learning process can give us. So the whole idea around intelligence amplification is about human and machines together are better than humans or machines alone. And this is kind of an analogy of this is like, you can dig with a shovel or you can dig with an excavator. So machine learning gives you the excavator rather than kind of digging by hand. So in spinal tap terms, it's kind of, everything goes to 11. So in the business world, our customers, the situation that we deal with is really, really high volumes of data. So when we look at all of the web behavior, transaction behavior, and so forth of our customers, there's billions of rows of data. You're integrating with different systems like web, email, transactions, call center, and so forth. And high rate of change. It might be 90, 100, 200 gigabytes of data coming in. And it's very dirty. So it has lots of noise in it and duplicates and so forth that we need to deal with. And with these systems, we apply the machine learning process to understand the consumer behavior, but it's really, really hard to do it in a structured approach or just a regular descriptive statistics approach, is because the consumer behavior, consumers never behave exactly the same way twice. And there's a lot of noise in that. So if you if two people browse the same product, one buys this one buys another one. So if you had a program that was going to do the same thing, it would have served two of the same stuff to these people. But by looking at the past and learning, you might understand that you can recommend stuff a little bit differently. If you even knew the customer, if you did know how customers are going to behave, you don't always have all the data. So there's a lot of missing data, and the computer programs are not really good at handling missing data, because if you have missing data, then there's no input to the system and you can't do anything. Whereas humans, we are great with, even if I see the partial face of my wife, I can still recognize her. And this is something that the machine learning algorithms do really, really well. And even if you had all the data, the underlying system changes all the time. So you might write a program that covers all the use cases, but the consumers change behavior, right? So the people who were buying in a certain way 10 years ago, now the millennials are buying completely differently. They do 90% of their research in a mobile device before even walking into a store, which is different than how 40, 50-year-old people buy today. And even if you could adapt to all these changes, there's a lot of useless data in this. So you need to basically eliminate a lot of the noise so that you're basically trying to find in this, what everybody talks about the word big data. Big data means that there's a lot of noise or unnecessary data in the system. So I'll give you one example from a real life customer where we're trying to segment customers. So we have this business that sells hair and beauty products, has a bunch of customers. They have about 2.5 or 2 million or so total customers, of which a couple 100,000 of them bought from them in the last few years. And the challenge was, you have very, very different people. You have young people buying cosmetics. You have people who are interested in more bath products. Some people are older. They're interested in wrinkle creams and so forth. So how do you group these people together in a way that kind of separates them out, so that when you communicate with these people, the way you talk to them, the way you recommend products to them, and so forth are very, very different. And so the whole idea around segmentation is taking a heterogeneous group of people within the context of the products they're interested in, and be able to kind of separate them into, okay, here are my athletes that are buying sunscreens and some other products and so forth that athletes buy. Who are my older generation people that are buying different things, and what are businesswomen buying that might be different as well. So this is a specific example that we're using, and I'm going to show you the results. I don't know if you can all see this, but this is what we call, we have this machine learning algorithm that groups people together based on their interest. And then the machine learning algorithm also creates what we call a DNA of a cluster. And the DNA identifies if you are in this cluster, if you belong to this segment, how much more likely are you to buy these products that you see on the x-axis than if you didn't belong to this cluster. So what this cluster is, general skincare cluster, where these people are 100% more likely to buy aging products and dryness and rehydration and basic care and so forth, but they're not really interested in like makeup and lip shines and so forth for that customer. Another example of this is another cluster called the Bath and Body cluster, which has 31,000 people in it that are here. And these people have 300 to 500% more likely to buy hair care and bath and shower gels, but they're not really interested in aging products and so forth. So these are just two examples of what we're talking about. So for those of you who are Instagramming, I don't see a lot of students here, so you guys were probably Facebooking. So just to summarize what I was talking about, machine learning is a very elegant way that solves complex problems that us as humans solve, but we're trying to take those complex problems at scale, detecting cancers or weather patterns or, facial recognition for detecting terrorists and so forth. There are many, many applications of this. Because machine learning is a great way of how it mimics kind of humans without having sort of explicit instructions of the thing. There are many stories where you'll hear that a class of machine learning scientists was able to do drug discovery better than people who were kind of experts in drugs. They didn't know anything about it, but they took the data and was able to kind of advance the process. And it's already changing, fundamentally changing many aspects of our daily lives. So even if you look at Google, how now we can do image search, some of the Google algorithms, they're already kind of transforming these things to deep learning. Google is in the forefront of this. And again, machine learning will be leveraged in any situation where we require trade-off or complex decisions and so forth. And some of the areas, just to give examples, is voice recognition in the call centers. Handwriting recognition is being used by USPS right now because if you imagine like how you want to sort these different handwritten kind of addresses, it's a huge expense to do it by hand, one-on-one. Sentiment analysis, drug discovery, machine learning will permeate across the board. But one thing that I certainly believe, which, if you read about this intelligence amplification, I don't think at any point it's going to take the human out of the equation. It will basically amplify humans' intelligence. And this is a very important factor to think because no matter how much this pattern recognition and learning that you can do, there's no machine that can be creative. The creativity part of human intelligence is incredibly hard to replicate in any sort of a machine situation. Thank you very much. I'll take any questions. Yeah.
Sorry. Thank you so much, Mr. Artoon. Unfortunately, we're a little bit over time, so we will not be taking questions in the auditorium, but Mr. Artoon will be outside for about the next hour and a half for a book signing. So you can ask him any questions you have about his presentation over there. So thank you very much.